Hello, everybody. Welcome to the third seminar this morning. We have a very busy day, very busy morning today. This talk will be given by Dr. Xiaojing Zhang Xiaojing. She's associate professor from the Qianxuesen Qianxuesen laboratory of CAS. The CAS. What's that? Must be
China Academy of Space Technology.
Okay, all right. He is her very brief biography. Dr. Zhang, she did her undergraduate in the China University of Geoscience, right? It's a地质大学, right?
是的 Yes.
在武汉. And did her undergraduate there. And then she went to the IGG, which is Institute for Geophysics and Geology and Geophysics.
Geophysics.
Of the Chinese Academy of Sciences in Beijing for her master degree.
Yeah.
And then after that, she went to get her PhD from Stockholm, University of Stockholm.
Yes.
Also in geology, right? Geological science.
Yes, always geology.
Right, and afterward, she did her postdoc at Nagoya. After Nagoya, and she came to Taiwan to work at the Institute for Earth Science of the Academia Sinica. I think you work with Professor Zhang
Qianxuesen.
Yeah. So she's sort of say one of us, you know, am I?
Yeah, absolutely.
and now she's back to Beijing, and she's building up her research group on planetary science, and she's especially interested in laboratory simulation. And she has built some cooperation with some the international teams. Dr. Zhang, why don't you tell us what's happening with your lab? Thank you.
Thank you. It's an honor to take part in this webinar this time. So my talk is I switched my previous, the title to Near Earth Asteroid Surface Property, because that's what I'm working on, the focus of my work. Then because, as you may have known from my background, I'm always a geologist, working on Earth stuff before switched to planetary science. So my ongoing work is still more to the geological side rather than this geophysics or planetary physics. I'm working with a bunch of engineers in CAST. So my research is kind of related to engineering, or how the hardware, the property associated with hardware design, and so on. Okay. First, my talk today will follow this background, include background first, and then some summary of this known knowledge of asteroid surface, and also then the last is my own work, then the summary. So the asteroids in the solar system, I think the asteroids are small rocky bodies orbiting the sun, and they have the size from meters to hundreds of kilometers, usually in irregular shape. So they are distributed mainly in the moon belt. Then we have our close neighbors close to the Earth. We call it near Earth asteroids. Then we have transient asteroids. The last talk is about. So the near Earth asteroids is very interesting to us because we might because they are close to us, it's easy to explore. And also we have potential to use their resources. They are also threatening the safety of the Earth. So it's always our interest. So they are from, where are they from? To put it simple, most of them are from the main belt because of this planetary migration, orbital disruption, also or Qianxuesen effects in Europe. They can gradually migrate from the main belt to the closed space of the Earth. Internationally, near Earth, asteroids are the hot topic right now because we have so many missions already. The Lucy is on the way. There are more planned missions in China mainland. We have Tianwen 2. It will launch in 2024 or 2025. I will talk about it later. And Psyche, the Comet Interceptor, DART, Hera, and so many others. So the China's asteroid exploration starts from Chang'e 2 in December 2012. Chang'e 2, after its journey to the moon, the Chang'e 2 successfully flew by these two TARDIS. It's a near-Earth asteroid. So it took the first close-up images of the asteroid for the first time. It looked like a ginger. Then the mission we are working on is called Tianwen 2 after Tianwen 1 to Mars. The China has named all its deep space missions in Tianwen. So Tianwen 1, 2, 3, 4. Then this mission is has two goals. We call it the 3M mission because first one is a multiple targets. The first target is a near Earth asteroid. It's called 2016 H03, and then it will return a sample from this NEA. Then it will continue its journey to the main belt to have rendezvous with main belt comet 1311P. Originally, the target is 133P, but then because of the timeline, 133P is not applicable, right? So we switched to our target to 311P. It's a multiple function. The mission will land, anchor, and sample the material from the surface of NEA. Then it probably will channel nanoprobes in the spacecraft. It's a multiple task: sample return, remote sensing, in situ measurement. So it's a multiple phase. Phase 1 will last 3 years, 2 to 3 years. Phase 2 will last 7 years. So it's very long journey to go. By returning a sample and making first rendezvous with the main belt comet, this mission aimed to explore the formation, evolution, secret information of the solar system, and to review the role of NEA and the main belt comet impact in the origin of life and the solar system, small body dynamics, formation, blah, 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 and so on. All these science information about our solar system. Of course, from the technical side, we have a lot of new technology documentation and demonstration during the mission. But there is a major challenge: the unknown property of our NEA target, the 2016 H03. It is a near-Earth asteroid of Apollo group. And so its formal name is this one, Como Live is a Hawaiian pronunciation word, but it's hard to pronounce. So I still call it 2016 HO3. So for short, it's HO3. So this HO3, as it orbits the sun, it appears to cycle around the Earth as well. So we call it a quasi-satellite of the Earth. What we know very little right now. We have this, we know how close it is to our Earth, and rotation period is about 28 minutes. So probably a S-type asteroid. You have this one or two single photometry and the reflectance spectra is, but with not very high precision. It might be S-type asteroid, but also later, like this year or last year, a new publication proposed it might be a lunar ejector. So it will be very interesting if it came from the Earth, the moon. So that makes our mission more meaningful, I think. The diameter is 40 to 100 meters. So that's what we all know right now. So what we need to know, especially for the sample return purpose, the physical property and the surface properties is really important, like how the morphology, the mineralogy, are there big boulders or small grains, and how the material strength and so on. So that's our motivation to for our research. Okay, so what do we know about surface property of NEAs? So far, I think we have 4 missions have on the near Earth asteroid. The first one is Shoemaker, it's Eros, and then we have in recent years we have Hayabusa 1, 2, and Osiris Rex to Itokawa, Ryugu, and Bennu. Eros is relatively different from the later 3 because Eros is much bigger. It's not much bigger, it's bigger. And then we have much bigger. Then Itokawa, Ryugu, Bennu are kind of in a similar size. And those 3 are revealed a very interesting structure. Like we call it rubble pile asteroids. As a rubble pile is an organized collection of microscopic particles. We call it maybe rubble, held by self-gravity and also as well as cohesion. And the size distribution of boulders and grains extends usually from microns to several meters. The density, we have very reliable data on the density of the 3 asteroids. Itokawa is smaller than 2 gram per cubic centimeter. So Itokawa 1.95, there's less than 1.5. If we compare them with the meteorites, they are corresponding meteorites. So Ryugu and Bennu are believed to correlate with CI or CM meteorites. They are like 2 or CI is 1.5. It's smaller, it's relatively small, but CM is 2 or 2.5. And ordinary chondrite is much larger. It's bigger than 3. So it implicates there are a lot of voids between the grains. Besides, their own a porosity from this rock. Then so asteroid macroporosity. There is some past study on this macroporosity of some asteroids. We can see they are grouped into 3 groups. the first one is the largest asteroids are intact bodies. This, the y-axis is the mass, the x-axis is the macroporosity, indicating almost no macroporosity. It's a typo. Then we have this 15% to 25% macroporosity in these smaller bodies. It indicating fracturing of the bodies, but some fracturing exists. Then we have these objects with porosity over 30. They are almost rubble piles. So the thing of yes. The Bennu, Itokawa, and Ryugu all belong to this part. And also rotation rate with asteroid size also sheds some light on this. We have this very famous diagram, asteroid diameter versus rotation period. We have this very interesting trend here. We call it a gravity spin barrier. No object larger than 1 kilometer in diameter like spin faster than 2.4 hours. So that's where it's here. So the big ones, the 1 kilometer, all spin faster, spin slower in this area. But then as it decreases, their spin rates can go up. So it means in this area, gravity dominates any strength effect. They can hold together purely on the self-gravity. But when it's been faster, when the size getting smaller, they have cohesive strength holding them together. So here is some calculation. If we take a weak lunar cohesion, 100 Pascal, that's a measurement from lunar samples. It's the green light. So that means if the asteroid green has cohesion has 100 Pa, it's not a very big number. So the most asteroids still can keep a rubble pile structure and rotate under those rate. And there's a lot of research has studied this cohesion between on asteroid material. We have this all these numbers here. Weak lunar regulates 100 Pa, and this from asteroid is around 100, a little bit slower than smaller than 100. So it's, of course, we don't now. Those values are quite wide. So with samples returned from Bennu and Ryugu, we are expecting we can get some real nice data on the cohesion force from those samples. Then we can have better estimation on the structure of asteroids. The numerical modeling of the cohesion in cohesion regulates of asteroids indicates rubble pile asteroid can be strengthened by cohesion force between their smallest grains. So if we use the lunar regolith cohesion value, so a 10-meter rubble pile can spin less than 5 minutes, even if there's monolithic borders in 10-meter size. It spins faster than 1 minute. The surface can still have millimeter to micron grains on their surfaces. So it indicates, so when we apply this knowledge to the HO3, so that's where it is. in the diagram. Like if we use lunar regolith cohesion to 100 part, it can have this, the red line is decimeter grains. It indicates its surface partly holds decimeter size grains on its surface. So our technicians working on the sampling mechanism will be very pleased. It's very pleased to hear that. If we take an example of a very interesting outlier, one asteroid is called 1950 DA. So this is a rubble pile because diameter is 1.3 kilometer, but its density is so low. Especially compared with its analog meteorite, is Easternite. So this density is 3.5. So we can see its macroporosity is very big. It's over 50. So it must be a rubble pile, but it's been pretty fast. Shorter than 2.4 hours. So it must have some cohesion force. Using simulation, we can get 64 Pascal cohesion force. It's in a reasonable range. It further indicates even in the left of the spin barrier, cohesion force, rubble pile can still exist. So the knowledge for 2016 H03 is it can be a rubble pile, and the decimeter grains can exist on its surface. Then we come to the composition, its surface composition. We have pretty good knowledge on the composition of asteroids. There are 3 lines of evidence. The first is the reflectance spectra. Since many years ago, like since the first observation of asteroids, and people have been observing them for many years, and we have compiled a lot of reflectance data for asteroids. So people then based on this data, asteroids usually have classified into different groups. There are several schemes for this taxonomic classification, but generally we can subdivide the asteroid into 3 groups: S group, C group, X group. S is linked to ordinary chondrites. It means stony asteroids. C is carbonaceous chondrite. Carbonaceous asteroid is linked with carbonaceous chondrite. X group contains metallic. Contains metallic asteroids, so it's linked with metal meteorites. The suspected composition is for S group is silicates, C group is hydrated minerals and organics. For X group is silicate plus metals. Then we have a big collection of meteorites. The ordinary chondrites and Easternite chondrites contains mainly olivine, pyroxene, mantle, sulfides. Volatile-rich carbonaceous chondrites like CiCm is the hydrated silicate, iron oxides, iron sulfides, and carbon compounds. And some other carbonaceous is CvCO, CrCkCH, mineralogy much like ordinary chondrites. The A chondrites are minor group, so they are igneous rocks from partial melts or melt residues. Then it's the irons and stony irons. It's usually iron, nickel, metals, and silicates. So the asteroids linked with them have the similar composition. Then we have the real information from real samples of asteroids. The Itokawa dust particles are the first ever asteroid samples back to Earth. So Itokawa, before the mission, Itokawa is was believed linked to S-type. Ordinary contract is S-type asteroid, and the study confirmed its link. It contains olivine, pyroxene, paleogeoclase, chalcite, chromite, iron, nickel metals. So it's very similar with LL chondrites, low iron, low mantle, low iron ordinary chondrites. The Liugu samples, the publication only has very preliminary results on the reflectance spectra of Liugu samples, but it has reviewed the Liugu sample are very primordial materials, like phenolcase, water-rich compounds and carbonates. It's very close to CI meteorite. But there are always something different. So the Hayabusa 2 and the OSIRIS-REx team have unexpectedly found the bright borders on their dark asteroids. The top are Liugu, the down here is Bennu. But these rocks are different, have different composition with carbonaceous chondrites. The Liugu ones, the bright blocks on Liugu is similar with Vista, with meteorites from Vista, like. And then the Bennu on the bright blocks on Bennu is S-type asteroids. It's linked with S-type asteroids. So we can, for asteroids, because it's an aggregate of different particles, you can expect to find something else. It's very interesting. Now we have the thermal inertia is a very useful measurement of materials resistant to temperature change. We can use this information to infer the presence of absence of loose material on the surface. The moon has 50, large main belt asteroids 10 to 50. Bare rock is hard rock is very high. Itokawa is this number. Bennu Liugu are very similar, around 300. Euro is 150. Moon is 50. So we all know the moon is covered by a very, very loose and fine green regolith. The Apollo samples, also Chang'e 5 samples. I think they are up to millimeter. Most are micrometer size, micron-sized grains. So it has very small thermal inertia. Itokawa and the Bennu Eros, so has loose material on their surface with larger grains, and also that's what we have seen on Eros, Itokawa, Liugu, and Bennu. Eros showed like fine material smaller than the centimeter size. Little cava is boulders and also fine grains on the surface. And the fines can be centimeter to millimeter. But Liugu and Bennu has much coarser boulders. They are the surface lack extensive areas covered in sub-centimeter grains. How the boulders and the fines formed, then we should look at the environment or the space weathering process on the surface of a planetary body. The first important process is called comminution. It's a random impact by small particles or debris found throughout the solar system. It can smash, break down big rocks into small pieces. Then because there's no atmosphere, and also so no protection from the solar irradiation. So irradiation by electromagnetic radiation or atomic particles from the sun, galactic source or magnetosphere can cause sputtering and charging on the surface, will destroy the atom and the mineral. So then, because it's near to the sun, when the asteroid rotates, the thermal stress can break down, make thermal fatigue during rotation can also break down minerals and the particles into small pieces. And the dehydration and converting dehydration process on the water-rich asteroids such as C-type, Bennu and Liugu can convert serpentine to polycrystalline olivine, then it also helps to break down the particles into small ones. All these process combined, the final result is the bigger boulders are slowly broken into small grains. The solar wind is a very important factor in the asteroid environment. It is a stream of charged particles released from the upper atmosphere of the solar corona. Most electrons, protons, and particles with thermal energy between lower than 10 keV is not a high energy, but the solar wind can have a pressure at 1 AU in the range of 1 to 6 nanopar. This force can work on the small particles on the surface of the asteroid and lift the particle into space. Because another very unique environment for the asteroid is extremely low ambient air gravity on the surface. It's called micro G. So because they are very small size, it's also close to the sun. It's the heliosphere is very small for NEA. The heliosphere is the gravitational sphere of influence of a small body in the face of a more massive body is in the sun. So we can guess when a small grain is lifted from the body, it can be very easy to leave the surface. The fine grains may also come from thermal fragmentation. The thermal fragmentation from diurnal temperature variation may break up rock surface more quickly than the impacts. then without a problem injecting from the low gravity body, creating fine-grained fragments. So that's a paper in Nature published on 2014. They performed laboratory experiments, also numeric modeling, and to show the carboniferous chondrites and ordinary chondrites their temperature varies a lot, and also they found temperature variation break down the CM meteorites very easily, because there's no shaking and no movement of this fine grain. They can keep on the surface instead of flying away. That's how the fine grains stays on the surface. But why the Bennu and Liugu lacks small grains? I think so. That's maybe because of the rock porosity. Those authors found they found the Liugu and the Bennu, the rock on the surface of Liugu and Bennu has much larger porosity compared with Itokawa. Itokawa is around 15 to 20. Like they have Liugu and Bennu has 50% porosity. Then the impact can compact the high porosity rocks. Then instead of break them down, and then the then the thermal fatigue work on the compressed rocks. So the thermal fatigue is not as effective as in S-type asteroid. So for small asteroids, low gravity, low escape velocity, and with much higher thermal inertia, they have solar wind interaction. So as asteroids get smaller, low gravity allows progressive larger ejecta debris to escape. So smaller asteroids usually have coarser regolith soil. The larger materials are retained, potentially creating we call it a lac deposit. The repeated disturbation causes overall slow motion in the downhill direction, forming this pond deposit. That's what we see on the small near-Earth asteroid regolith surface. But fine grains appear to exist under the lac. So Hayabusa impact experiment revealed under the boulders there are fine grains. Probably because the boulders on top of the fines protect the further lift of the fine grains. Then we can have a look at the asteroid meteorite streams. This is a nice summary of the on the streams measurement of meteorites. So most of ordinary chondrites is like a Itokawa type asteroid are very tough. That's the here the HLL. So it's up to 100 to 1000. But volatile-rich carbonaceous is CMCI. They are very weak. You can, if you hold one piece of CI, you can crash them. It's very much weaker. So volatile-rich pore, the CV, CO or CV, they are can be as strong as the ordinary chondrite, but not still lower than ordinary chondrite. So what's our work is enlightened by this previous research. Because I work with a bunch of engineers and technicians, they are concerned on the surface property of asteroid. So my work is focused on developing regolith simulant. We have developed a series of simulant, including the S-type, C-type, Main-belt comet, and also we have created a Rubble structure in the lab to test the hardware and also the remote sensing instrument like a camera, and reflecting and the spectrometry and so on. So that's the reflectance spectrum of our S-type simulant. So it's very close to the S-type asteroid and also Itokawa. So very good match. Also, we have conducted some preliminary measurements on the cohesion force by the atom force microscope. So the sample is our regular simulant. The green side is here. It's about 25 micron. So under the ambient condition, the force is this, and under vacuum is half of the force. So if we assume the greens are spheres, so the cohesion is 21 Pascal. Then if the diameter, we take diameter of 20 HO3 is 40 to 100 millimeter. So there will be borders at up to meter size at the equator. So that's the implication from our measurement. Also, we have conducted some uni-axis compressional experiments on chondrite. It's a LL chondrite. It's linked to S-type asteroid, probably the HO3 type. So compressive strength is 75 megapascal. It's not very high. And so we can also see how the fractures grows under the force. And then further work is about the thermal fatigue effect on this sample is ongoing. So we are applying the thermal cycling in this sample for multiple, like several hundred cycles to see how the strength will change. The work is still going on. So hopefully one day we can present the results to audience, to people who are interested in. Okay, we have some conclusions for small asteroid regoliths. It probably will be much closer than lunar regoliths. Border coverage. The surface fines will be depleted by the solar wind, but fine grains can exist below the boulders and the cobalt. It's most NEA rubble piles. There will be space weathering effect on the grain. Come to 2016 HO3, what's the implication? So we can expect could be a rubble pile, a surface covered by regolith layer with decimeter to meter sized grains. Probably we can have fine grains below the lag surface if we also make a hole of this surface. It's possible to find the flat sampling area if it's a irregular shape. And then we need a very good control of the authority. Small asteroids eject particles probably due to this electron-statics effect. Type of the mineralogy are still not very sure, but it's likely S-type. So the rock should be stronger than Bennu and Liugu. But I think the boulders and the cobbles on the surface of this asteroids will not be as strong as an ordinary contrast because it has undergone space weathering, the thermal effect, the plus impact. There will be fractures in the boulders. So I will estimate it's maybe less than 100 Pascal compressional strength. I think it's a good news for the sampling mechanicals designers. So I think that's all.
Yeah, thank you, Xiaojing, for this very interesting talk, introducing what is it called now? The mission Tianwen is it Tianwen-2?
Tianwen-2.
Why is it called Tianwen-2? You have Tianwen-1, right?
Yeah, Tianwen-1 is to the Mars. We have two series in deep space exploration missions. The first series, Chang'e, designed for lunar missions. So all the lunar mission we'll call Chang'e 1, 2, 3, 4, 5, 6. And then the others beyond the mission beyond the lunar, beyond the moon, is all called Tianwen.
So the Jupiter mission will also be called what, the Tianwen-3?
I don't know if it is 3, but will be called Tianwen something, some number.
That's pretty boring, I tell you.
Yeah, that's not what I can decide. It will be very confusing.
Yeah. Okay. Let's see any questions from the audience. If you have questions, please ask Dr. Zhang, and anything that she could tell you all the secrets there is, for the asteroid mission. Lin Qihong, please.
Okay, so good morning. So I have one question. So just like you say, there's a thermal variations to cause there's a thermal force that might be destroys the stone in the asteroid surface the faster compared for the small meteor come from the space. But my question is that because we know most asteroid their surface can keep the stable just like this maybe billion year, but most asteroid their surface is not smooth. They still has many large stone. So why is a large stone that can be survive in asteroid surface as long time and didn't destroy by the thermal variation? Is that mean that kind of stone inside is something like metal, this kind of material? Because we know the metal this is elastic and it can be bearing this kind of stress more a long time compared for the common stone.
Yeah, okay. Thank you for your question. First, you say the surface age can be billion years. I mean, asteroid, it's from the birth of the asteroid. Of course, it's a billion. It's as can go back to the origin of our solar system, but the asteroid's surface age is usually pretty young, especially in the near Earth space, because they can survive usually some million years, 10 million. It's in million years, because it will then eventually it will be disturbed by the sun or leave our crash into the Earth or crash into the sun. So it can survive very, very long in the near Earth space. That's why I think one reason for the big rocks can be found on the surface. Also, I think your reason, I mean, what you are saying, the mental content can be a factor for this.
So which type of material they can be bearing this kind of thermal force the longest time? So might be is the main component of the bake storming the asteroid surface.
Can you repeat your first sentence? I didn't really.
If you want, you could ask the questions in Chinese.
我们知道就是就像您刚才所说的，小行星它表面的石块，它被热应力破坏的速度可能会比被流星体砸坏的速度还要快。但我的问题是呢，因为我们知道小行星表面的这些物体可以持续存在几亿年，它可能都不会变化。但小行星表面它不是平滑，它还是有很多大石头。那为什么这些大石头可以存在那么长的时间？是不是可能因为这些大石头它可能里面有很多金属，就是像铁或镍？因为我们知道铁跟镍它对这个它的强度很强，所以它可以承受更多的热应力，然后比较不会被破坏。因为像砂岩或者是橄榄岩这一种石头，它是很脆，可能应力超过某个阀值之后它就会破坏。但是金属它具有塑性的特征，就是应力超过它的强度之后，金属的形状可以改变，所以可以吸收应力。
是这样，就是小行星形成的时间，它的年龄可以长到就是太阳系起源，但是它的表面时间，它暴露时间，然后到了我们的近地空间，实际上时间是比较短，它们的近地的时间的这个寿命还是比较短的。因为我们说起来这个温度的具体的变化，也就是说你离太阳越近，当你自转的时候，你的变化越大，所以我们主要是考虑近地空间上这个温度的变化。那么它们小行星在近地空间的存活寿命一般是100万年纪，而不是1年纪，所以它的时间其实上没有那么长。所以因此对于这个造成的变化可能是累积起来，也没有说把所有的东西全部都 crash into small pieces。
但对这些材料来讲，100万年可能也是一个非常长的时间，也足以把它们全部破坏掉了。
那我很难，那我不太，这个我就不敢说是不是一定可以，但它肯定是不会像我们发现的这个地球上发现的陨石这么强，已经是这么强的这个 strong 了。毕竟它在上面肯定有裂纹，或在表面上有裂纹，它如果是个很大的话，它也是需要很长的时间。具体这个时间长度上我不好说，还是要看看那个真正的计算和观测和计算结合起来。
Okay, let's switch back to English. Wendy, Professor Wendy Zhang has a question, and then comes Casey. Yeah, Wendy, please.
Hi. So I have one naive question. So
nothing's naive.
Okay, so because we know the small asteroid has a very small gravity, or say almost zero gravity. So I'm curious if in your measurements or the experiments or simulations, could you find the effect of gravity on the cohesion force? Or, I mean, what's the difference between, result from the gravity, like the difference gravity on Earth or on the microgravity like on asteroids? So what is the major role of the gravity played in the cohesion force or something like that?
Oh, pardon me for a minute. My AirPods are running out of power. I have to switch.
Just hold on, wait until Dr. Zhang Xiaojing, get power up again. Are you ready now? She's trying to power up. Her earphone has not enough electricity, so she's coming back. She said.
Okay.
Okay,
Am I
fine, yeah.
right now?
Yeah, we can hear you, yes.
Okay. You mean the gravity effect on cohesion force, right?
Yes.
I mean, the cohesion force is basically is the wonderful force. But on the Earth, when we can't, I mean, when we measure the cohesion force, we can't rule out the influence of gravity. Because we are in this Earth environment. So I don't know how to answer your question, actually.
Okay, you invite Wendy to visit you.
Sure, sure.
I'm happy to.
Okay, Casey, you want to ask the question in Chinese or in English?
English, please. If you don't mind. I wanted to thank you for your excellent talk. I've just learned a lot. And I wish I'd heard it before. We just published a new paper on why Phaethon is so blue. And Phaethon is a small asteroid that comes the closest or almost the closest to the sun of any asteroid. And it's extremely blue. It isn't just neutral. It's actually a bluish green if you looked at it. And our best understanding and arguing from the same curves we used to actually understand Arakoth is that it gets so hot, about 1100 Kelvin on the surface, that you remove all the nanophase iron and all the refractory organics. So you remove all the effects of space weathering. I didn't know about the fact that you might actually remove water from the phyllosilicates and that you could crack things open. So I'm going to go and look up the Delbo papers that you just referenced and try to understand them better.
Okay,
yeah,
Casey, you're also invited to visit the Professor Zhang.
I mean, that's why, I mean, geologists should work with the planetary scientists, and also we should work together on this.
Yes, in fact, I think you've been working with Dan Brent on the simulant, because I know he was talking to some of the groups in China. I was supposed to talk to groups. I was actually invited to go to Wuhan.
I invited him come over now 2 years ago. Before, I mean, that's before the
pandemic.
It will be the COVID-19 thing.
I was supposed to go to Wuhan and actually work on Comet simulant, but that kind of ran into the COVID. So yes, I've been talking to Dan about his simulants. But I'd very much like to talk to you maybe offline afterwards about what you think might be happening at Phaethon.
Oh, that's nice. I'm happy that. Okay, I mean, yeah. If there's no more questions, you can always write to me if you have any more thoughts and questions on the comment. Yeah.
Wing, will these slides be available? You can certainly have mine.
You mean what?
Can we share the talks?
I think so. I think they are recording the talks.
Oh, well, that's good enough. Mm-hmm.
Yeah, and it will be available online or what?
Yeah, yes, we will be do it online in few days, so we will have a link to everyone. Yeah.
Very good.
All right. In case no other questions, and I think that the case is sleepy and we are hungry, and so I think we have very, very exciting morning this morning and learning a lot. And thank you so much, all the speakers. And want to thank Professor Xiaojing Zhang again, and thanks. And hope to see you next time. Bye bye.